Our next presenter is Andrew Branch of NASA JPL, and he'll be talking to us about onboard autonomy requirements for an Ocean World's submersible mission. Andrew.
Yep. Can you hear me?
Yes, we can hear you.
Great. As he said, I'm Andrew Branch from the Artificial Intelligence Group at NASA's Jet Propulsion Laboratory, and I'll be talking about these onboard autonomy requirements for Ocean World submersible missions. So first, next slide, trying to control it myself. So first, some background that I'm sure most people here know, but just in case, ocean worlds are bodies in our solar system that are thought to harbor liquid water oceans, often encased in icy shells. In the case of, say, Europa, we're talking in the tens of kilometers thick. However, they are one of the best chances for extraterrestrial life in our solar system, so they're of extreme interest for scientific study. Next slide. So to actually study these subsurface oceans, subice oceans on ocean worlds, a new mission concept would need to be developed, specifically an Ocean World submersible mission. You can see a very high-level concept of what such a mission might look like. Over here on the right, it would be longer duration mission. To get through that icy shell, it's going to take maybe a year or more. Then once you're underwater, you want to spend, say, a year underwater exploring the area around your borehole through the ice. Ideally, you'd travel up to hundreds of kilometers from the base station. Now, if you look at the subsurface ocean depth, we're talking in the 80 to 100 kilometer range. So to even get down to the seafloor, you're looking at traveling 100 kilometers vertically. This type of mission would likely have three main components. One, a surface antenna, which would be able to talk direct back to Earth. An under ice base station that's deployed at the bottom of your borehole that has a number of communication instruments on it. And then obviously the submersible itself deployed into the ocean. So the submersible would have likely an acoustic link to the base station for acoustic communications, and then some sort of link from the base station to the antenna, back to Earth, giving you a complete communication pathway from your submersible back to Earth. However, you would have fairly limited communication windows due to orbital occlusions on the orders of tens of hours for both Europa and Enceladus per orbital period. And if you're far away from your base station outside of acoustic communication range, you obviously wouldn't have any communication to Earth. Additionally, you are in an ocean, which is a very dynamic environment. So this prevents kind of the traditional human-in-the-loop operations that you see for surface missions like Mars rovers, where the vehicle is expected to mostly maintain a very similar state to when you left it last. So due to these two constraints, full autonomy would be needed for potentially weeks or months at a time. Next slide, please. There are a number of requirements that this autonomy system would need to handle if you're trying to maximize the science return that you can get from such a mission. The first of which is autonomous science. So, if you can only periodically talk to your spacecraft, you need some way to discover and track any scientific features of interest. And you need to decide when you want to use any expendable science experiments that you might have. Now, scientists on the ground would still be able to guide these decisions as they would periodically get data back, but being in an ocean, you need to make much of these decisions by yourself, being in that dynamic environment. Second, autonomous navigation. So the submersible needs to know roughly where it is in the water, and it needs to be able to come back within at the very least acoustic communication range to your base station to talk back to Earth. Depending on how the mission is designed, you might have to do some sort of autonomous docking to do faster data transfer, or maybe charge the vehicle. activity planning, so deciding when do you want to do science, what science do you want to do, or you'll have competing science objectives that you need to decide between. When do you return for communications, and when do you do any maintenance activities and other any other activities that need to be done to keep the spacecraft alive. And then finally, autonomous fault recovery. Once again, you may be outside of communication range at some points during the mission, and you can't just go into a safe mode and wait for humans to come in the loop. You have to actively come back within communication range before you can actually talk back to Earth. So I think really the best way to understand these requirements better is to just talk about some of the work that we've been doing towards achieving them. Specifically, I'll be talking more about these first two here at the top, the autonomous science and autonomous single beacon navigation, as that's what we've been focusing on. So for the rest of the talk, I'll be talking more about the algorithmic side of those than actual implementation, because as you can imagine, an Ocean World submersible mission is quite far off in the future. And so we're working on doing testing here on Earth, and the implementation for AUVs on Earth compared to the implementation for a space mission. The connection there is potentially a bit tenuous. So if we go to the next slide. So first, talk about autonomous science. So this, as I said, is in short detecting and tracking scientific features of interest autonomously. There are a number of different scientific features that scientists may be interested in. So this requires encoding some sort of expert knowledge about that scientific phenomena into autonomous algorithms. Hydrothermal venting is just one phenomena that we've focused on. There are many others that have different signals and different algorithms that would need to be developed to target individual features. But for hydrothermal venting, this is what we've been working towards. So hydrothermal venting is particularly interesting because it harbors unique ecosystems that are based on chemosynthesis instead of photosynthesis. So if you're out in the outer solar system, there's not a lot of sunlight to support life. And then there's the potential for hydrothermal venting on Europa, and actual evidence that hydrothermal venting is active on Enceladus at the seafloor. And then finally, the sensors that are actually used to detect hydrothermal venting are all low power, low volume, low mass sensors. So temperature, oxidation reduction, potential, and optical backscatter, all relatively easy to put on an Ocean World AV. Next slide. So hydrothermal venting has this particular structure where the hydrothermal vent is on the seafloor, and it's expelling chemically altered seawater. So hot, low density fluid that exits this vent and is buoyant because it has lower density than the surrounding area, forms this buoyant plume, then spreads horizontally to form this non-buoyant plume once it reaches equilibrium. So you can actually use this plume to track back to the vent site, and then once you're close to the vent site, that is where kind of these fairly unique environments are found. So next slide. So this problem of locating these hydrothermal vent sources can be quantified a little bit more here, where the objective is to estimate the location of this vent site while minimizing the search time that it takes to actually find that vent site. And to do so, you'd use a number of measurements in the hydrothermal plume fluid, a number of measurements to determine the hydrothermal plume fluid concentration to actually localize this vent source. So sampling through that hydrothermal plume. This is complicated by a number of factors, mainly tidal and turbulent flows that kind of disrupt nice smooth gradients and different vent sites and number of vents that are all unknown are all unknown when beginning this search. Next slide. So we've developed a number of search methods here, which I'll very briefly discuss, but not really in too much detail. So first here over on the leftmost side, we have the kind of a nested search method, which is based off of how hydrothermal vent search algorithms actually are used in Earth's oceans, where you're doing kind of these lawnmower patterns of increasing resolution and decreasing size to locate the hydrothermal vent source, kind of focusing where you see maxima in those measurements that I previously stated to kind of characterize the hydrothermal plume. Next is what we've called the greedy transect method, where you're just kind of performing this star pattern at some location, and if you see new max locations, you perform that star pattern again until you've reached some maxima. And finally, a fairly straightforward gradient ascent method, where you calculate the gradient and follow it upwards. So as you can imagine, all three of these methods are relatively light on computation. Obviously, there's a number of other methods that you could employ that use, complex machine learning and all kinds of computationally expensive algorithms. However, those would likely be difficult to implement on a processor that would actually be feasible on a Ocean World's AUV, where power is so constrained. Next slide. So we have been able to deploy these on an AUV in 2019 in Chesapeake Bay, on an Ocean Server Ivor 2 AUV with the Naval Research Laboratory. This is a very lightweight, short-range AUV, not extremely representative of what you would use on an Ocean World, but real hardware in the water. We were running on a rather powerful backseat, running an Intel Core i7, 4 gigabytes RAM, and just Ubuntu. This is significantly more computational power than we actually required, but these are the kind of systems that are often put into Earth-based AUVs nowadays. This backseat was running Moose IVP so we can talk to the front seat, get all the data that we need from the vehicle itself. And unfortunately, as you might imagine, Chesapeake Bay has no hydrothermal vents in it. Hydrothermal vents are the closest one off the contiguous United States is probably axial seamount, a couple 100 kilometers offshore, which is difficult and expensive to get to. So we had a realistic simulated hydrothermal vent model running on board the vehicle to provide simulated data. Next slide, please. And here we can see some results from this deployment and also some simulation results, some full simulation results. So from the deployment, you see on the left plot, the vehicle goes and performs these large lawnmower patterns, and then performs recursively these smaller and smaller patterns to pinpoint the vent location. And then kind of in deployment and full simulation results, we were able to successfully find the hydrothermal vent with these different search methods. Some, as you can see over here, significantly more successful than the others, but with that higher success rates comes the downside of longer search times. So all those would need to be balanced in an implementation on an Ocean World submersible, where you're competing with other science objectives and communication power constraints much more than you would be on an Earth-based AUV. Next slide. So now I'll be briefly discussing the autonomous navigation methods. So autonomous navigation, there are a number of instruments on board AUVs that are used for navigation. These are listed here. So you have some sort of depth sensor, an IMU, magnetic compass, Doppler velocity logs, which give you velocity relative to either the water, the sea ice, or the seafloor. These are active sensors, so they are large power consumption devices. And then finally, acoustic beacons, two different types. One, ultra short baseline, providing range and bearing with a kind of one single beacon, providing both range and bearing, and other beacons that just provide range calculated from the time of arrival. So no bearing, just ranges. So everything in green here, you would expect to have on an ocean world submersible mission. The Doppler velocity log here in yellow, it's a large power consumption device, so you will likely have one, but won't be able to use it all the time. And then finally here in red, a magnetic compass. You may or may not be able to actually have a magnetic compass. Europa has an induced magnetic field from Jupiter, so it's time varying, and whether a traditional magnetic compass would function properly is sort of unknown, or if you could model that time varying magnetic field and then use a compass along with that model is also a bit unknown, but it's very possible that no magnetic navigation will be possible. Next slide, please. So we've identified kind of three main navigation paradigms that would be of interest for an ocean world submersible. So when you're close to your beacon, say, these are very notional distances, I should say, because underwater acoustic propagation is quite complex. But say you're less than 10 kilometers from your beacon, then you'll likely have range and bearing from your single acoustic beacon using one of the ultra short baseline beacons. But those use ultra short baseline frequencies, so very high frequencies, so they only operate at shorter ranges. So once you get a little further away, you'd expect it to still have ranges from acoustic beacons, but only providing range information, no bearing information. Since this is only using time of flight, you can use much lower frequencies and get much longer ranges out of it. So you're only getting ranges, but you kind of need to figure out your bearing based on what ranges you're receiving. And then finally, when you're, say, greater than 100 kilometers away from the base station, you'll have no acoustic communication, so you're just running off dead reckoning, and where this is really only feasible for short periods of time. It's also worth noting that an ocean world's AUV would need to be able to autonomously transition between these three different paradigms, as whenever you're transitioning between them, you're going to be outside of acoustic communication range. Next slide. So we're really focusing on that middle paradigm there, where you have a single acoustic beacon with only ranges. When you're really close, the problem's sort of already solved. When you're really far away, there's really not that much you can do. You're just dead reckoning and deciding when to turn around and come back so you can feasibly return within acoustic communication range. But there's but for that middle region, there's a couple different methods that we're looking at. One is synthetic multilateration, so having a bunch of these ranges, and you take ranges you receive ranges at many different locations, and you use dead reckoning to track the relative positions of those ranges, and then you can use some nonlinear optimization to find where they all mostly intersect, and that's where your beacon is. And then the other method, which is a bit of a more simpler method that doesn't actually give you your beacon location exactly, is to use something like golden selection search, where your vehicle is traveling along a specific heading and is calculating the rate of change of ranges as they're received, and you're trying to maximize that rate of change of range, or minimize, if you're heading towards the beacon, I guess, that rate of change of range. Next slide. So we've been able to do some testing with this on the Tethys class long-range AUVs provided by the Monterey Bay Aquarium Research Institute. And this is running, this was run on Jetson Nanos, on a Jetson Nano, so quad-core arm, downclock to 918 megahertz for to reduce the power consumption, as this is a long-range vehicle, so power consumption is a lot more important here than it was for our other deployments. Next slide. So we have some initial results from that deployment and from simulation. So in that deployment, we were able to test just the synthetic multilateration methods, where we were able to, as you can see here up on the right plot, we perform these circles while getting ranges, and then use nonlinear optimization to target, to locate the beacon location and then home towards that beacon location, as you can see here. So we were able to do so successfully when using compass data. And it says here that it is ongoing work to improve the compass system performance. But since actually making these slides, we've done some post-processing of that data, fixed a few bugs that actually shows that we were able to also successfully home using without using a magnetic compass, just using your IMU and angular velocity data. Then on the second method, the golden selection search method, so far we've only been able to do in simulation testing here, but we've seen successful homing in this simulation with variety of sensor uncertainty parameters, where you, as you would expect, as your uncertainty increases, your performance, how long it takes to actually do the homing, decreases. Next slide. There's a number of related works for all this work that's been done. If you're interested further, next slide. So the future work for kind of Ocean World's AUVs and these methods specifically are to kind of demonstrate these autonomous methods combined. It's easier to do them individually than to do everything together at once, to demonstrate this autonomy in under ice conditions here on Earth, specifically enabling long duration deployments. If you can't do it here on Earth, you're not going to be able to do it on the ocean world. And start investigating these other autonomy requirements that I discussed, such as activity planning. This type of work's been done for other space missions and for some other AUVs and a couple other places, but we're looking to apply that specifically to the Ocean World submersible mission problem. Next slide. That's it. Yes, so that's it. So now I can take any questions if there are any.
Excellent. There are a few questions. First question is, what is the main source of power and how do you handle autonomous power management?
That's a great question, and that's still an ongoing problem. There are a number of studies. I think there's one study that's been done that basically says the only way to get enough power is to put an RTG on board. Whether that would go on the base station or on the submersible vehicle itself, on the base station and then have some charging mechanism. I don't think that's, those types of details aren't really figured out for these missions. But you would likely have some sort of RTG, which when you're operating in an ocean, planetary protection isn't too fond of that. That's a problem that needs to be worked out. And then how to manage autonomous power? How do you autonomously manage power? That's a great question, and I'm not sure any work has been done towards that. I don't really have a good answer there because, yeah, I mean, I just don't have a good answer. But that is a very important component that would need to be included.
All right, next question from Guillermo. Do you see any possible turbidity of the surface ocean as a risk for the autonomous algorithms and the scientific return of the mission?
So the yes, so on the science side, specifically for hydrothermal vents, turbidity is seen in hydrothermal plumes. So on Earth, that's used as a measure of, hey, we're in a hydrothermal plume because of the of the turbidity that we see. But I think this brings up a good wider question of what's the conditions of that you're going to be operating in an ocean, in some ocean world's ocean, right? We don't really know what an ocean world ocean's like. You might have, like you said, big turbidity issues and not be able to see very much. You might, what's the density is going to be like? What's what's the water composition going to be like? Nobody really knows. So the only real answer for that is to have some precursor mission that is able to access the ocean and observe its conditions to really understand the operation, the environment you'll be operating in, and then you'll have to design around those particular issues. I don't really see any other way to plan around that, because nobody knows currently what's going to be there when you get there.
All right, excellent. And there are a few additional questions that we'll bring over to Slack. And now we'll take a 5-minute break. But thank you very much, Andrew. Excellent presentation.